In the second part of Mod 6, we are going to be proving identities. And the first one we are going to look at, we need to prove that the quantity of 1 minus cosine squared times secant squared equals tangent squared. When you are trying to prove identities, you want to work on the side that's more complicated, which in this case would be the left side. Look for Pythagorean identities and see if you can put those into play somehow. If all else fails, turn functions into sines and cosines and see what you can get out of that. So the first thing that I notice on this identity is that the quantity of 1 minus cosine squared is one of the versions of the Pythagorean identity. We know that 1 minus the cosine squared equals the sine squared. So we're going to replace 1 minus cosine squared with what it's equal to, sine squared of x. Then the other thing, when I look at secant squared, I remember that secant is the reciprocal of cosine. So I can rewrite secant squared as 1 over cosine squared x. Now what we do is put the equals on the right, saying we're going to show you that this left side will equal this right side. So now sine squared times 1 over cosine squared, if you do the multiplication, you get sine squared x over cosine squared x. But we know that sine over cosine equals tangent, so sine squared of x over cosine squared of x equals tangent squared of x. And then to complete our proof, we say that tangent squared equals tangent squared. On example B, we want to prove that the sine squared of x minus the cosine squared of x equals 1 minus 2 cosine squared of x. So in looking at this, I'm going to change the left side into the right side. And when I look at the right side, the only function that appears on the right side is cosine squared. So when I look at the left side of this function, I have to ask myself, is there a way I can remove sine squared and replace it with cosine squared? Well, I have a Pythagorean identity that sine squared equals 1 minus cosine squared. So that's what I'm going to do. I'm going to replace sine squared with 1 minus cosine squared. Those two things are equivalent to each other. And then I'm going to keep my minus cosine squared that I already had. Well, now I have minus cosine squared minus cosine squared. So if I combine my like terms, I have 1 minus 2 cosine squared x equals what I already had on the right side. On example C, we want to prove that the secant squared of x plus the cosecant squared of x equals the secant squared of x times the cosecant squared of x. Well, in looking at this, we want secants and cosecants on both sides. So we're not going to convert anything. What might be helpful on this one instead is to use the reciprocal functions, what we know about secant and cosecant. We're going to rewrite the secant squared as 1 over cosine squared. And we're going to write cosecant squared as 1 over sine squared. Well, now we have two functions with two different denominators. So we want to find the least common denominator. When you have denominators that are completely different from each other, your LCD is the two multiplied together. So our LCD is cosine squared times sine squared. What that means for the first fraction, it's missing the sine squared part of the LCD. So we are going to take the first fraction times what it's missing, sine squared of x. But if you're going to take the bottom times sine squared of x, you must take the top times sine squared of x. On the second fraction, it's missing the cosine squared portion. So we are going to take that fraction times cosine squared over itself. Now remember, anytime you're taking a fraction times something over itself, you are taking it times a 1. So it will look different, but it will have the same value. Now, multiplying fractions, you go straight across. So sine squared times 1 gives me sine squared x over the LCD of sine squared x cosine squared x plus 1 times cosine squared gives me cosine squared x over sine squared x times cosine squared x. Well, now that we have the same denominator, we can add the fractions. And fraction rules say that you add the numerators, and because they are not like terms, we have to leave it separate, and put it over the same denominator that you already had, sine squared x times cosine squared x. When you see sine squared plus cosine squared, that needs to jump out at you that equals 1. So we now have 1 over sine squared x cosine squared x. We're getting really close here to getting what we need. We need to get to secant squared times cosecant squared. And if we think of this now as two separate fractions of 1 over sine squared x times 1 over cosine squared x, here we are just using fraction rules and splitting a single fraction into two separate fractions. But what do I know about 1 over sine squared? I know that that equals cosecant squared x. And 1 over cosine squared equals secant squared x. Now the other side had it written in the other order. And if you want to turn it around to make them match exactly, you can, but you do not have to. Once we had it at cosecant squared times secant squared, we had done our proof. On example D, I chose to do this problem because this is a problem that uses a very common technique in doing proofs of trigonometric identities, but it's not a technique that you would think of if you haven't seen it before. So I wanted to make sure that I showed you one like this. When we look at this, we have all different kinds of functions here. We have cosine, we have sine, we have secant, we have tangent. So we got to somehow do something to change these things around. The other thing to notice is that nothing is squared right now. So we have no Pythagorean identities that will help us in any way. So one of the things that we can do to create a Pythagorean identity is when we have an expression in the denominator like 1 plus sine of x, we can use its conjugate, and that will create a Pythagorean identity for us. So our first step will be to leave the fraction alone. Just leave it as cosine x over 1 plus sine of x. But now we're going to take it times the conjugate of the denominator. A conjugate is the same terms, but you change the sign between the terms. So we're going to take it times 1 minus sine x. But remember that anything you do to the bottom, you must also do to the top, so that you are taking times a 1, and you have not changed the value of your fraction. So let's do this multiplication. We are not going to actually multiply the cosine of x times the quantity. We're going to leave that alone. We're going to leave that as cosine x times 1 minus the sine of x. But on the bottom, because we are taking 1 plus the sine of x times 1 minus the sine of x, we have to do FOIL. If we take the first times the first, we get 1. From the outsides, we get minus sine of x. From the insides, we get plus sine of x. And from the last times the last, we get minus sine squared of x. Well, if you look at this, plus sine of x and minus sine of x equals 0. So we now have cosine of x times the quantity of 1 minus sine of x over 1 minus sine squared of x. What's convenient about this new denominator is that this is a Pythagorean identity, and we can replace it with what it's equal to. So we're going to leave our numerator alone and put it over what 1 minus sine squared equals. That equals cosine squared. Well, now here's another little trick that you maybe wouldn't think of if you hadn't seen it. We're going to split cosine squared into cosine times cosine. So we're going to have cosine x times 1 minus sine x over cosine x times cosine x. Well, cosine over cosine is 1. So now what we have is 1 minus sine of x over cosine of x. We are getting really close. If you look at the right side, we want the terms of secant and tangent. So what we're going to do to get us to that is we are going to use fraction rules and split this from one fraction into two separate fractions of 1 over cosine of x minus sine of x over cosine of x. Well, what do I know about 1 over cosine? It equals secant of x, and sine over cosine equals tangent of x. And that is where we were supposed to be, equals secant of x minus tangent of x. So we have completed our proof. On example E, we have the secant of negative x over the cosecant of negative x plus the sine of negative x over the cosine of negative x equals negative 2 times the tangent of x. What you need to recognize on a problem like this one is the first thing you must do is use your even and odd identities. Remember that the only functions that are even are cosine and secant. And so what that means is when you have secant of negative x, that is equal to just the secant of positive x. When a function is odd and you have a negative on the argument, on the x, you pull the negative sign out front. So the bottom will become negative cosecant of x. On the second fraction in the numerator, you have sine of negative x. Sine is an odd function, so this will become negative sine of x over, your denominator is cosine of negative x. Cosine is even, so it just becomes cosine of positive x. So if you look at the fraction on the right, we already have sine over a cosine, which is a tangent. We're looking good there. The problem is the fraction on the left, where we have secant over cosecant. So what we're going to do is use the reciprocals here. We know that secant equals 1 over cosine of x. We know that cosecant is 1 over sine. So because that's negative cosecant, we're going to have negative 1 over sine of x plus negative sine of x over cosine of x. We haven't changed our second fraction. When you are dividing fractions, you multiply by the reciprocal of the bottom. So the left-hand fraction will become 1 over cosine of x times negative sine of x over 1 plus negative sine of x over cosine of x. Well, now multiplying the fractions on the left, we will get negative sine of x over cosine of x plus negative sine of x over cosine of x. So as you can see, we are getting there. So now we have negative tangent of x plus negative tangent of x, which gives us negative 2 tangent of x equals negative 2 tangent of x. On our last proof, we need to show that 1 minus the cosine of negative x over the secant of negative x minus 1 equals the cosine of x. Again, because we have negative arguments, the first thing we want to do is use even odd rules. Cosine and secant are both even. So the first thing we're going to do is rewrite our left fraction as 1 minus the cosine of x over secant of x minus 1. We want to get to a cosine of x. Our numerator already has a cosine of x in it. And when you look at the denominator, it has secant, which we know is the reciprocal of cosine. So we're going to leave the numerator alone as 1 minus cosine of x. We are going to rewrite secant as 1 over cosine of x minus. Now let's think about this. We're going to need to subtract these two terms, and we've already turned the left-hand term of secant x into a fraction. So I'm going to also rewrite 1 with a denominator of cosine x. Well, in order to make 1 with a denominator of cosine x, your numerator must also be cosine x. So now we have a complex fraction where the numerator is 1 minus cosine x, and then the denominator is a fraction of 1 minus cosine x over cosine x. We subtracted those two fractions in the denominator using fraction rules. Well, now we have a complex fraction, and when you have a complex fraction, you always multiply by the reciprocal of the denominator. So the numerator is going to stay 1 minus cosine of x. We're going to take that times the reciprocal of the denominator, which is cosine x over 1 minus cosine x. If we think of that first term as being 1 minus cosine x over 1, we can, as you like to say, cancel and take 1 minus cosine over 1 minus cosine. That equals 1. And so what are we left with? Just cosine of x equals the cosine of x, which is where we were going.